double dash is equal to S1. So, we know again two properties. So, we can find out rest of the properties. And point 2 dash is nothing but saturated vapor at 50 degrees centigrade. So, you can easily find out the properties, other properties. And point 1 dash is the saturated liquid at minus 25 degrees centigrade. So, this point is uniquely fixed. So, you can find out all other properties. And point 4, at point 4 you know the pressure PE, and you also know that it is an isenthalpic process. So, the enthalpy at point 4 is same as enthalpy at point 3, that means H4 is equal to H3, which is known. So, you again know everything about point 4. So, you can find out rest of the properties. Point 4 dash, as you can see from the drawing, has same entropy as that of point 3, that means S4 dash is equal to S3. Okay, so the which is known to us, and we also know the pressure at this point. Okay, that means from the given information you can find out the property data at all these points. Okay, so now let me show this property data. Before that, this is the summary of the information given. Refrigerant is 134A, evaporator temperature is minus 25 degrees centigrade, and condensing temperature is 50 degrees centigrade. Okay, and the property data, as I have already explained, is like this. This is the exit of the evaporator or inlet to the compressor. We know this temperature and quality, so we can find out the pressure, saturation pressure, and then we can find out the enthalpy and entropy from the pH chart or from the TS chart or from any other database. Next, point 2. Point 2 is the isentropic compression. We know the pressure, which is corresponding to 50 degrees centigrade, saturation pressure corresponding to 50 degrees centigrade, and we also know that it is isentropic process. So, the entropy is same. So, these two are known to us. So, find the rest of the properties. Similarly, point 3. Point 3 is the exit of the condenser. We know the temperature and we know the quality. So, find the pressure, find the enthalpy, and find the entropy. Point 4, okay, it is the exit of the isenthalpic process. So, the enthalpies are same at point 3 and point 4, which is known to us, and we know that the temperature is minus 25, which is same as the evaporator. Pressure is now also known to us. So, from this we can find out what is the entropy. Okay, and you can also find out the exit quality from these enthalpies. And point 1 dash is saturated liquid at evaporator temperature. So, you can find out easily enthalpy and entropy. Point 2 dash is the saturated vapor at 50 degrees centigrade. You can see that saturated vapor, quality is 1, temperature is 50 degrees, pressure is 13.18. So, you can find out the rest of the properties. Point 2 dash, 2 double dash, at this point we know the temperature, which is equal to 50 degrees, and we also know the entropy, okay, because this lies on the constant entropy line. So, this is known to us, this is known to us. So, rest of the things we can find out. Finally, point 4 dash, at point 4 dash we know that the temperature is minus 25, and we know that at this point the entropy is same as that of point 3. Okay, so, this is same as 1.37. So, we know the two properties, so we can find out the rest of the properties. So, that this is how we found the properties at all the points. So, once you find the properties at all the points, you can easily calculate COP. COP is nothing but refrigeration effect, H1 minus H4 divided by specific work of compression, that is H2 minus H1, which is found to be 2.1174. Then work input to compressor is nothing but H2 minus H1 from energy balance across the compressor, so which is found to be 52.8 kilojoule per kg. Then we have to find the superheat horn area. Okay, superheat horn area is area A1, and it is nothing but area under 2 dash minus area under 2 double dash to 2 dash. Okay, let me explain this. Okay, so this is the superheat horn area, the hatched area. Hatched area is nothing but area under 2 dash, that means the complete area, this entire area, minus area under 2 double dash to 2 dash, that means this area. Okay, so if you can find out the area under curve 2 to 2 dash and subtract the area under the curve 2 double dash to 2 dash, you get the superheat horn area. Okay, and this is an isobaric process, that means P2 So, I will quickly explain how we can calculate this superheat horn area. Process 2 to 3 is an isobaric process, that means P2 is equal to P2 dash, and remember that we know all the entropies and all the state point properties are known to us. So, area under the curve 2 dash, okay, area under 2 dash is nothing but integral TdS from 2 to 2 dash. Okay, and from thermodynamic property relations we know that TdS is equal to dH minus VdP. Okay, so if you are applying this relation to this particular process 2 to 2 dash, you find that VdP is equal to 0 because the pressure does not change during this process. This is an isobaric process. So finally you find that TdS is equal to dH. That means integral TdS from 2 to 2 dash is nothing but integral dH from 2 to 2 dash, which is simply equal to H 2 dash minus H2. Okay, if it's as simple as that. So if since we know the enthalpies, we can easily find out, and this remember is nothing but the entire area, okay, under the curve. And what is the area under curve 2 double dash to 2 dash? Area under 2 double dash to 2 dash is nothing but this rectangular area. Okay, so which is equal to again integral TdS from 2 double dash to 2 dash, and this is an isothermal process, so temperature remains constant. So this is simply equal to Tc into S 2 dash minus S 2 double dash. Okay, and we know the entropies at these points, and Tc is known to us, so we can also easily find out this area. Okay, so it's very easy. We just find out the area under 2 dash and the area under this one, and subtract these two areas. You will get the superheat horn area. Okay, now how do you find the throttling area? Okay, throttling area can be obtained in by two ways. Okay, the first way is if you are finding the proper throttling area is this. This is nothing but throttling area from this expression is nothing but CD 4 dash, or nothing but the rectangular area, and this is equal to, again if you are applying integral TdS, temperature remains constant, integral TdS from 4 to 4 dash. So this is simply equal to TE into S4 minus S4 dash. Again we know all the entropies, so you can easily find out the throttling area using this expression. You can also use the find out the throttling area from this side. Okay, because if you are assuming this line to coincide with the isobar at PC, this also happens to be the throttling area, and if this is the throttling area, okay, if you are calculating it from this side, this is nothing but area under 3 to 1 dash, area under 3 to 1 dash minus area under 4 dash to 1 dash, 4 dash to 1 dash, that is this area. Okay, and area under 3 to 1 dash, you can see that for this again area under 3 to 1 dash is integral TdS from 3 to 1 dash, which is equal to, again you can use the expression dH minus VdP, TdS is VH minus d, and since we are assuming that this line is an isobaric line, VdP is 0. So this simply becomes TdS becomes equal to dH. So finally this is nothing but H3 minus H1 dash. Okay, so we can easily find out, and this rectangular area, that is area under 4 dash 1 dash, is nothing but TE into S4 dash minus S1 dash. Okay, so that's how once you have the cycle diagram, you can easily find out the required areas. Okay, so that is what is done here. Okay, so I have explained this procedure. All this is shown to you, and if you are substituting the values, you find that area under 2 dash is found to be 12.8 kilojoule per kg, and area under 2 double dash to 2 dash is nothing but the rectangular area, is found to be 12.6 kilojoule per kg. So from these two we find that the superheat horn area is equal to 12.8 minus 12.6, that is 0.2 kilojoule per kg. Okay. Now let us find out the throttling area. So as I have already explained how to find the throttling area. If you are assuming that the saturated liquid line is coinciding with the isobar at condenser pressure, then it is the area under 3 to 1 dash minus area under 4 dash 1 dash. Okay, so this is the expression, area under 3 to 1 dash is nothing but H3 minus H1 dash, and area under 4 dash to 1 dash is nothing but TE into S3 minus S1 dash, because S4 dash is equal to S3. Okay. So since we know all these values, you substitute these values, you find that the throttling area is 14.47 kilojoule per kg. If you are finding the actual throttling area without making this assumption, then that is given by area under 4 to 4 dash, which is equal to TE into S4 minus S4 dash, and this works out to be 14.4 kilojoule per kg. You can see that the assumption that the isobar coincides with the saturated liquid line is reasonably good, because these two values are perfectly matching. Okay. Now you can also check the your results, because we know that for the single stage saturated cycle, the work input is equal to work input of a Carnot cycle plus area A1 plus area A2. Okay. And what is the Carnot cycle? Carnot cycle here is an equivalent Carnot cycle is 1, 2 dash, 3, 4 dash. So this is your Carnot cycle. So find out what is the work done during this Carnot cycle. Work done during this Carnot cycle is nothing but this, okay, which is equal to Tc, this is Te, this is equal to the rectangular area, that is Tc minus Te, into this entropy difference. Okay, that means S1 minus S4 dash. We know all these things. You can easily calculate the work input to the Carnot cycle, and work input to the actual cycle is work input to the Carnot cycle plus this area plus this area. Okay, so you can check your result. So if you are doing that, work input to the Carnot cycle is found to be 38.2 kilojoule per kg, and work input to the standard cycle from this expression is 38.2 plus 14.4 plus 0.2, which is working out to be 52.8 kilojoule per kg, which matches exactly with the data obtained earlier. Okay. Now you repeat this problem. The homework is like this: repeat the problem by replacing R134A with ammonia, and you compare the performance, and you conclude by comparing the results obtained with R134A and ammonia. Okay, so there will be some differences because ammonia has a different TS shape. Okay, vapor dome shape is different on TS plane for ammonia and 134A. Okay, so this is the homework, right? Now let me quickly give some objective type problems for your homework. Okay, so objective problems are like this. First problem is, which law of thermodynamics is a directional law? The answers are: A is first law, B second law, C third law, fourth zeroth law. Okay. The second question is, according to second law of thermodynamics for a system undergoing a process, entropy of the system cannot decrease, that is A, and B is entropy of the system cannot increase. C is the sum of entropies of system and surroundings remains constant, and D, the sum of entropies of system and surroundings always increases. And third question is, expansion of liquid always results in a significant temperature drop when the initial condition is in subcooled state, the initial and final conditions are in subcooled state, the final condition is in two-phase region, and none of the above. And fourth problem is, during isenthalpic expansion of a real gas with negative Joule-Thomson coefficient, the final temperature is lower than initial temperature, the final temperature is higher than initial temperature, the final temperature is equal to the initial temperature, and finally nothing can be said about the temperature. And problem number 5, the COP of a completely reversible single stage refrigerant system depends only on the evaporator and condenser pressures, depends only on the evaporator and condenser temperatures, depends on the working fluids and operating temperatures, and all of the above. Okay, I will give the answers to these problems in the next class, and I will also work out 1 or 2 problems on vapor absorption systems in the next class. Thank you. Welcome back. In this lecture, I will work out few more example problems, and I will also give answers to the questions given in the last lecture. So the first, let us go to the first problem. The first problem is like this: in a R22 based refrigeration system, a liquid to suction heat exchanger with an effectiveness of 0.65 is used. The evaporating and condensing temperatures are 7.2 degrees centigrade and 54.4 degrees centigrade respectively. Assuming the compression process to be isentropic, find specific refrigeration effect, volumic refrigeration effect, specific work of compression, COP of the system, and finally compressor exit temperature. And comment on the use of liquid suction heat exchanger by comparing the performance of the system with a SSF cycle operating between the same evaporator and condensing temperatures. That means basically it is a single stage system. We have to make performance comparison between a system with liquid suction heat exchanger and a system without liquid suction heat exchanger. Both of them are operating between the same evaporator and condensing temperatures. Now let us see how. Then work of compression. Work of compression, obviously with liquid suction heat exchanger, work of compression has increased because the isentropes in superheated region are flatter compared to the isentropes closer to the vapor dome. So this is 36.1, this is 31. So this is actually a negative this thing. And COP you can see that is almost same, okay, it is 4.465 with liquid suction heat exchanger, and it is 4.455 without liquid suction heat exchanger, okay. This is because COP, as you know, is the ratio of refrigeration effect divided by work of compression. So when you are using liquid suction heat exchanger, refrigeration effect is increasing, work of compression is also increasing, okay. And without liquid suction heat exchanger, this is less. At the same time, work of compression is also less, okay. So as a result, the net difference between these two is not much, okay. And however, one significant difference between the system with liquid suction heat exchanger and without liquid suction heat exchanger is in the discharge temperature, okay. You can see that with liquid suction heat exchanger, discharge temperature is about 105 degree centigrade, whereas without liquid suction heat exchanger it is about 74 degree centigrade. That means almost more than 30 degrees increase, okay. So this is definitely a negative point as far as the liquid suction heat exchanger is concerned, okay. So you have when you are using liquid suction heat exchanger, particularly for R22 systems, there are some benefits and there are some disadvantages, okay. So ultimately, depending upon your requirement, one has to decide whether liquid suction heat exchanger is required or not.